Good morning. I welcome you all for the lecture series in Mechanics of Solids. Today we will discuss about bending stresses in beams. In the previous lecture, we have studied shear force and bending moment. In this lecture, we will go through with this bending stress. So bending stress is critical in structural engineering. Beam resists bending loads in bridges, buildings, and machines. Accurate bending stress calculations ensure safety and optimal design. So understanding the basic stress concepts, stress is force per unit area measured in PSI, KSI, or pascals. Normal stress includes tension and compression. Shear stress is another type of stress. Hooke's law relates stress to strain. So stress types, normal and shear. Key concepts is stress is force per area. Hooke's law states that stress is directly proportional to strain, where E is the modulus of elasticity. Bending stress, the core principles or key assumptions include a straight beam and homogeneous material. The neutral axis has zero bending stress. Bending moment is the internal moment from external loads. The initial assumptions for calculations is the beam is straight before bending and after bending, and there exists an axis where zero bending stress point. That axis is called neutral axis. And the layer is called neutral layer. And the bending moment is the internal moment due to loads. So the flexural formula explained is sigma equal to m by I into y. Sigma is the bending stress, m is the bending moment, and y is the distance from neutral axis. I is the area moment of inertia. So stress at specific point can be calculated using the notation sigma. Internal moment at the section can be calculated with the bending moment m, and distance from the neutral axis is y. So calculating area moment of inertia is crucial for bending stress. Formulae vary for different shapes. The parallel axis theorem handles composite shapes. Rectangle I equal to bh cubed by 12, circle equal to pi d power 4 divided by 4 into 64. Composite shapes, we use parallel axis theorem. Flexural formula, step-by-step examples. So calculating maximum bending stress in beams, determine support reactions, draw shear force and bending moment diagrams, find the maximum bending moment. So support reactions, let us consider a beam which has a point load at the center, and the beam is to be simply supported beam. And we have first, in simply supported beam, we need to calculate the support reactions RA and RB. After finding the RA and RB, we need to calculate the bending moment and draw the shear force and bending moment diagrams. From the bending moment diagrams, we can calculate the maximum bending moment of the particular beam with the load. With that maximum bending moment, it is possible to find the bending stress using flexural formula. So real-world bending stress applications, bridges, buildings, and machine components rely on bending stress analysis. Consider bridge beams under traffic loads. Design floor beams to withstand occupancy and loads. Bridges, traffic load analysis, buildings, floor system design, machines, stresses in rotating shafts. So in the third application, the rotating shaft is tend to bend whenever there is a load. So that comes under bending stress. So the key takeaways and design considerations are accurate stress calculations are vital in design. Material selection impacts bending resistance. Considers safety factors and design codes as per AISC Euro code. So the first part is stress calculation that is crucial for safety. The second part is material selection that impacts resistance. And the third part is safety factors that explains the design codes. So these are all the key takeaways from this lecture. So even though we calculate normal stress and tangential stress, the bending stress is required to ensure safety and optimal design. So this is all about bending stress. So I thank you all for this patient listening. We'll continue flexural formula and its problems in the next forthcoming lecture series. Thank you all.